Okay, the next part of approximating area under the curve, so part 2. In this lesson, we're going to have a more formalized technique on how to do this. And so just how could we possibly make improvements? So keep that in mind as we work through this of how could we make this better? How could we, improve upon our approximation as we head down this path? So first thing we have here is the graph of f of x equals x squared shown at the right. It's for x is greater than 0. So they started at 0 and showed us the right side of x squared here. But notice that the interval 1 to 3 is divided into 4 sub-intervals. So what they did is they took the interval from 1 to 3 and they divided it into 4 equal pieces. Kind of looks like a bar graph. So carefully copy the graph on your graph paper and use this equation to obtain the coordinates of the points where the rectangle should touch the curve. So going to do the best I can here of trying to graph this. So if we look here, right, and we have the point 0, 0, right, 1, 1, because x squared, right? So f of x equals x squared, right? So if we're graphing this, right, 0 plugged in gets me 0, 1 gets me 1, 2 would get me 4, 3 would get me 9, right? So 2 we would be at 4. And then at 3, we would be at 9. Okay, so kind of running out of room there. So we can see here this curve as it goes up. Okay, so now then we need to divide this into sub-intervals. So here's the best way to do this, okay, is to take your interval, which is 1 to 3, subtract it, right? That's a distance of 2, and then divide it by the number of pieces, right? So there's 4 equal intervals. So the width of my interval is 1/2. That's the width. Okay, so let's see if we can draw some rectangles here. So if we start at 1 and we go over 1/2, that's 1 rectangle, right? The next rectangle is going to start at that same 1/2 spot. It's just going to touch the curve, right? And it's going to go over to 2. The next interval is going to start at 2 and come down. And then the next one's going to start at 2.5 and go over to 3. Okay, so if we're looking at those intervals, right, and we're changing at a width of 1/2, okay, what we're going to do there is start with 1, and our next point would be 1.5, and then 2, and then 2.5, and then 3. So you're saying, hey, coach, but those are 5. That's 5 numbers, not 4. You said 4 equal parts. Correct. 4 equal parts in the sense of that's a part, that's a part, that's a part, that's a part, right? So 4 parts, but 5 points, right? So when we label these points, we're labeling this x0, or our starting point, x sub 1, x sub 2, x sub 3, and x sub 4. Okay, and so as we do this, right, as we label, B then says, in terms of rectangles drawn, what does the y value of each coordinate represent? Well, so I haven't found the y values. So let's find the y values here of each coordinate of those points on the line. So 1 is on the line, so we can see that right here. Okay, that's a point on the line, right? So 1, 1, right? The next one would be 1.5. right? Well, where would that be at? Well, 1.5 squared, right? You have to put it into the function, right? 1.5 squared, right, actually gets you 2.25. Okay, 2 squared is 4. That would be the next point in the graph. And then 2.5 squared is 6.25. Okay, so what are those y values? It's the height of the rectangle. So we already know the width of the rectangles. That's a half. Okay, but the height of the rectangle is where that y value is, right? So the y values are the height, or length times width, right? Base times height. That we're getting the area. Remember that, right? So what's the width of each rectangle? We already found that, right? Subscript notation is what I just talked about down here. So this is your subscript notation for each interval. Okay? So that's what that is there. I don't know what I did, sorry. The 4 shaded rectangles in the diagram are called left endpoint rectangles. Well, why? Because if you look at this rectangle, the left endpoint, right, is the one that's touching. It's on the left. Okay? Now, approximate area under the curve. So let's try to do this. Let's try to create an area under the curve feel here. So how do we do this? Okay? So if we're trying to create area under the curve, right? So I'm going to use sigma notation to do this. So what would we do there? We would take the height times the width, and 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 we would add them all together. Well, we've already learned summation notation. So let's look at this. If this is x sub 0, we're using that one. We're using 1, we're using 2, we're using 3. So our sum is going to go from 0 to 3. Okay, and just for reference, those are left endpoints. Left, left, left. Well, what would you do in right endpoints? Okay, you would come from the right. Okay, so you would go from here, right, 2, 3, 4. So from the left is always going to be 0 to just one less than the rectangles. Okay? If it's from the right, it's going to be from 1 to the number of rectangles. So we'll come back to this here in a second. But from the right, it's going to be x equals 1 to 4 for this problem. Okay? Well, what are we summing? We're summing area. Area of what? Rectangles. Well, what is the area of a rectangle? Okay, well, the area of a rectangle is length times width, or base times height, right? So for us, we already know the width, and it doesn't change. So the width is 1/2. We're going to go ahead and put that in our sum, right? Both of them are the same. So we're putting that in. Now, the length or the height, right? Base times height, right? The height changes. And it changes based on the formula of the line or the curve or the equation. But here's how is it changing? That's what we have to figure out. Well, it's a linear change, right? It's the width. It's changing 1/2 every time. So it's starting at 1. So this is a linear change. So think like y equals mx plus b. It's a linear change. So what are we changing? We're changing 1/2 every time. And then, coach, we're starting at the value of 1. So this is our changing equation. This is how it changes. Okay, but we need to take that equation and plug it into our function to then figure out where those points are. Okay, so we're taking this 1/2 x plus 1 and we're plugging it into the function. Well, that means it's this squared. Okay, if it was x squared plus x, we would have to say plus 1/2 x plus 1. We'd have to put it again, right? So everywhere there's an x, you will plug that into your equation. That changes formula. Okay, so it's the same formula over here, right? 1/2 x plus 1 squared, right? Same formula. We just changed our starting point, right? 0 to 3, 1 to 4. So we actually now have done, right, left endpoint and right endpoint for both of this. Okay, now we haven't drawn right endpoint rectangles, but we have the summation for it. So then we can just put in the summation. Okay, and so as we put in those summations, here's what we're going to get. So for the left, you're going to get 6.75. For the right, you're going to get 10.75, right? And when you put those in the calculator, that will work. So you should be able to see here that the left, right, if I zoom in, right, the left is an overestimate, right? Like there are points missing here. So if you look, there's space here that's not accounted for, right? It's less, so it's an underestimate. So if we go back, right, we know this is underestimate, right? So the right's going to be an overestimate. So let's look at the right. So let's see if we can find a color that works here maybe. Okay, so let's draw right endpoint rectangles. So we're going to start from the right. Well, can't get it to move. Okay, so from the right, we're going to start here and go right and draw that rectangle and this one. And again, guys, these go all the way down to the x-axis, right? So right endpoint and right endpoint. So you can see the first point we start at there is actually this 1.5. So again, it goes back to, what are we using? 1.5, 2, 2.5, and we're actually using 3. So we're going from 1 to 4, which we've already done, right? And if you sum these up, I promise you will get the same thing here. And if you don't believe me, try it for yourself, right? So 116 just talks about how can we determine, right? So if you look at a curve, if the curve is increasing, left endpoints are going to be an underestimate. Right endpoints are going to be an overestimate. If the curve is decreasing, right endpoints are an underestimate. Okay? Left endpoints are an overestimate. Right? So that kind of answers your question there of 116, right? Okay, here. So let's go to 117. Let's a little bit closer, right? So what happens when you change this to a bunch of rectangles? So same graph, same interval, we're just changing the width. So if you count here, there are 8 rectangles. So this time, since there's 8 rectangles, let's find our width. So again, 3 minus 1 over 8. So we got 2 over 8. Our width becomes 1/4. That's our width. Everything else should stay the same. Now we're going to have to change our changes equation, but so we have summation from 0 to 7. Coach want 8 rectangles. Okay, so our right would be sum from 1 to 8. So left 0 to 7, right 1 to 8. Okay, our width comes next, so we write our width, 1/4. And then we need to come up with that changes equation. How does it change? So again, mx plus b, our width is 1/4 every time, and our start is 1. So that's our changes equation. But remember, that has to go into our function. Our function is x squared, so we're putting this into x for x squared. So 1/4 x plus 1 squared. Same here, 1/4 x plus 1 squared. So again, if we sum those, we get a little bit closer. So when you do these, you actually get, I think it's 8675, something like that. 10.8675, something like that. It's very close to that. I may have those decimals wrong, but it's very close. Okay, so you're getting closer. So then they just talk about what changes from left to right. So from a left endpoint to a right endpoint, the only thing that changes there is just your what you're putting into your summation. So again, 0 to 7 or 1 to 8. And so I've already 120, it says right in summation notation. Already done that for you, right? Just having the idea of being able to do that and then using your calculator then to solve it. So yeah, 3.2.3, part 2 of area under the curve.